I'm glad to announce our next speaker for the BIMS Integrable System seminar. It's Xuantong Qu, who will speak about special functions on finite Chevalley groups. Thank you very much.
Yep. Thank you so much for the introduction, and thank you so much for the invitation to this great seminar. I have to announce first that this is my very first time to give a research seminar talk. So I would like to thank everybody here and online for coming to my debut. And just one warning for the people just joining this meeting, this is not the end of my talk. Today, I would like to talk about some special functions over finite Chevalley groups. So as we know, that special functions appear in many interesting areas of mathematics, including integrable systems, and also like in automorphic forms and arithmetic geometries. And today, I would like to share with some my recent works on special functions, studying special functions in terms of representation theory, in particular, theory of finite Chevalley groups. This is my preprint. And so let's start with some very simple example of special functions. Even simple enough, we could observe something non-trivial. So for like complex number with positive real parts, one naturally have the notion of gamma function, which can be studied as functions satisfying this functional equation or interpolates of factorials. And naturally we have this integral representation of the gamma function. From this integral representation, we already see some interesting properties in terms of representation theory. For example, the first factor appearing in the integrand is actually the multiplicative character of the field of real numbers. And the second factor is indeed the additive character of the field of real numbers. And this whole integration is taking over the identity component of the non-zero real numbers as a topological group. Throughout this talk, we will see that actually all these properties listed here has its finite field analogues. Moreover, we can see more using like representations of finite groups, as we will see later in the talk. So a second example of special functions is the Bessel equations, coming from studies of this differential equation. And as we know, long time ago, is the solutions to this Bessel equation has this kind of integral representation. And this integral representation has many interesting interpretations in terms of representation theory and quantum integral systems. So today I will mention one work by Bernard Constant, who identifies these Whittaker functions in terms of representations of this SL2, special linear group over the real numbers. And in particular, in his paper, Constant studied these Bessel functions in terms of quantum integrable systems. To be honest, I'm not an expert in integrable systems, so I will come to that point. I will briefly explain Constant's construction of this Bessel function in terms of representation theory. And it may take some time to explain, but it's nice to talk about it first, because we will see that actually its construction can be transferred to the finite Chevalley groups, and we can and has this proper analog over finite fields. So consider the SL2R, well, which just 2 by 2 matrix with determinant 1. And we consider the induced representation from the Borel subgroup of SL2. Throughout my talk, I will always assume that the Borel subgroup is some lower triangular matrices. And since we are working with real numbers, so we need to be careful with the character we choose, but this is fixed. And of course, throughout my talk, most of the representations I consider will be this regular action, which is rate multiplication of the function. And in this particular case, this representation space, this induced representation space, also called B equivariant vector function spaces, it has a non-degenerate pairing, or in short terms, we can say one can define an inner product on this representation space, and this integral is taken over the maximal unipotent subgroup of SL2R. Indeed, what Colson did is to identify this Bessel function with this matrix element or matrix coefficient, which is a pairing that I showed on the last slide, and a pair of vectors. Here we take these two pair of vectors to be same, and sorry to abuse the notation because because later I will use it again and again for something else. But what I would like to emphasize is that this function in this representation space, also called Whittaker vector, satisfying this property, which is eigenfunctions with respect to the action of maximal unipotent subgroup. And I use the notation psi because I will, throughout my talk, I will use psi to denote some additive character, which this function is indeed determined by the additive character of the field, whatever we are considering. And from this expression, actually, we can already see a lot of interesting properties of this Bessel function, because it's a matrix element for proper chose this parameters mu and epsilon. Actually, this is a unitary operation, and moreover, is for this matrix element, for this property of psi, we see that this function is indeed bi-equivariant under the action of this maximal unipotent subgroup. Actually, this idea of identifying this matrix element where one vector is the Whittaker vector is due to Hervé Jacquet in his PhD thesis. But actually, he considered another vector in this path, namely the spherical vector. By definition, it is invariant under the action of the maximal compact subgroup of SL2R. Namely, in this case, it is the special orthogonal group or the rotations on a plane. And actually, up to some normalizations, these two functions these functions are coincide. And as you see, actually, by the Iwasawa composition of SL2R, we see that the value of this function is indeed determined. This function is indeed determined by its value on the maximal split torus of SL2R. But we will now come back to this point in the rest of the talk. So this idea of Whittaker choice of Whittaker vectors actually play an important role in many constructions over the real numbers or the finite field number that I will explain later. So what happens for finite field? Throughout my talk, I will fix FQ to be a finite field of Q elements. And here, I require this Q to be odd number. In other words, the Q is a power of a prime, of an odd prime number. So the characteristic of the field is always greater than 2. And one can define this so-called Gauss sums as a finite field analog. And as you see here, actually in this expression, we see that the first factor is an additive character. We define this to be an additive character of the finite field, and the second factor to be the multiplicative character of finite field. If In particular, we choose these two characters to be non-trivial. Otherwise, if one of them were trivial, actually what we obtain is the so-called orthogonality of one-dimensional representations over a finite group, which is not so interesting to study. And of course, this value, if both multiplicative character and additive characters are non-trivial, actually we got some interesting values. In particular, like, for example, like it appears in the proof, in Gauss proof of quadratic reciprocity. And moreover, one can see that the Gauss sums appear naturally in the context of finite field Maillard transforms and discrete Fourier transforms. For this discrete Fourier transforms, actually is defined analogously to the Fourier transform over the real numbers, and which can be studied in many contexts in arithmetic geometry due to various people. For example, Audrey Turas, she has a very interesting textbook introducing this notion, and Gauss related this finite field Maillard transforms to the study of arithmetic monodromy groups. So it has many interesting aspects to study this notion of finite field in many mathematical contexts. Moreover, one remark about this definition is that if we change our additive character a little bit, namely, we define this multiplicative character psi b by simply multiplying a non-zero element in the finite field. Actually, this again defines another non-trivial additive character over the finite field. And if we substitute this psi b instead of psi into this formula, we obtain the following identity of sums. Please note that this can be viewed as a finite field analog of the functional equation of gamma function. Namely, we do some multiplication on this additive character, and then on the other side of the equation, it is a multiple of the multiplicative character of the finite field, which share the same formalism as the situation of the real numbers. Up to this point, all we are discussing is we view the finite field, both additive group and multiplicative group, as a finite abelian group. So of course, that's very classical theory. What about we move to, maybe I walk a bit further. What about we move to the non-commutative case? Namely, we consider a very simple non-commutative group, the affine group over Q, which is a semi-direct product of these two subgroups, this U and this A. And here I have abuse notation again because this psi as a character on this group U is actually determined by its value on this entry X, which behaves like which is isomorphic to the additive group of the finite field. So I use this same notation to psi to denote the character of this group U. And the same for A. The value of this character on A is can be defined by chi of Y for non-zero element over finite field. So so actually from this simple like semi-direct product, we already constructed something non-commutative, but using the blocks of this to components of to group structures appearing in the finite field arithmetic. And in this setting, we consider this induced representation. which is indeed irreducible by some representation theory of finite groups. I will not get all the details here, but actually this is simply looking. Well, representation space has dimension q minus 1, and it is irreducible. And a surprising fact about this this special representation is that the Gauss sum is the matrix element of this representation space, of this representation, which again, as I mentioned earlier, the action of the group, acts by right diagonal action. In the rest of the talk, we will see some similar construction to this, this identification with the matrix element. But we will change the group and indeed the representation space a little bit, and we will see that in the induced representation from this maximal unipotent plays an important role in different contexts of representation theory. So before I go into this point, I would like to state another finite field analog of Bessel functions, which is indeed the Kloosterman, so-called Kloosterman sums. This Kloosterman sum appears like in many contexts of mathematics. Here I listed two, like automorphic forms and arithmetic geometry, because it's well known that actually this sum over a finite field is proposed, well, by Kloosterman first, to study the circle method in analytic number theory. But then later it's like, Andre Wei gave an explicit estimation of this one in order to prove some special case of his Riemann hypothesis over the finite field for curves. And later in the 1970s, I believe, this simple looking sum is related to the three coefficients of Poincare series by several works of Ivanich, Goldfield, and many other people. So I will briefly review some properties of this Kloosterman sum in terms of representation theory of finite groups, and to convince you that this one is actually a proper analog of Bessel functions that I show in the beginning of my slides. So one observation is that we can do something similar as cosine construction. Namely, we have the Whittaker vectors for representation, principal series representation of GL2. And one can identify this sum as values of the matrix element in terms of these two pairs of Whittaker vectors, and it looks like this one. When we restrict ourselves in the big broad cell of GL2 or FQ. Over the broad small cell, actually, this is not something interesting. We just get a product of multiplicative characters, and provided that the values here to be different, otherwise we get 0. This is nothing interesting. But in this way, we connect this trigonometric sum with as the values of a special function over this finite Chevalley group. actually, exploiting this idea, we can find something more interesting. Namely, we can associate this Kloosterman sum with the Gauss sum that I introduced minutes ago. Namely, there's a famous note by Shapiro when he gave lectures in Tel Aviv, Israel. And he studied representation theory of GL2 over a finite field. And well, I mean, Gauss sums and Kloosterman sums over finite field in the same time. And one key observation in his notes is that by using the finite field analog of this Whittaker vectors as constant exploited, one can study a lot of properties of this special functions over GL2 in terms of its representation theory. In particular, this Whittaker model, which I will explain for GLN later of my talk. So what Shapiro really showed that is the Kloosterman sum. Well, where I wrote has a special value of this matrix element equals to some normalization constant. We can ignore it at first. But the non-trivial fact is that this is a sum over all multiple characters, but the integrand is a product of two Gauss sums. And this is not a trivial fact that why these two trigonometric sums or exponential sums should be related in this way. And this is a kind of more surprising fact that this is indeed a finite field analog of integral representations of the Bessel function when we take the special parameter as this equation shows. Actually, you see that this one is a product. In the integrand, there appears a product of two gamma functions as I explained earlier, the finite field analog of the real number counterpart of our finite field Gauss sums. So actually we see that this this Gauss sum I show here is merely an analog of gamma functions in terms of its formalisms, but they do share some similar relations and their interpretations in terms of representation theory. So let me state carefully about how Whittaker function is constructed for a Chevalley group. Here we just take that to be GLN, the general linear group over a finite field. So speaking of the characters of the multiplicative subgroup, we always fix this one to be in this form, which you can see that this is the sum of all entries on the superdiagonal. Some people call it like this. And we take the additive character over the finite field. And we will always fix this character throughout the talk. And it might be interesting to take something else, which is called degenerate one, but we will always stick to this particular character. And again, we consider the induced representation from this maximum unipotent. And this is first studied by Gareth and Gray in 1960s. Originally, actually, their work concentrates on SRN, so the special linear group over finite fields instead of general linear groups. And they prove some very interesting results I will explain later, but most importantly, that works for GRN. And maybe one thing worth to mention is that the general construction for all the reductive groups over finite field, this induced representation is again multiplicity free due to the Robert Steinberg's lecture at Yale University, and his title of the lectures are called lectures over Chevalley groups. That's why I use this name in my talk. So since this representation is multiplicity 1, which means each entry has which means every irreducible representation of GRN only enter once in this large representation space, and if a irreducible representation could embed into this Garfunkel representation, we call this representation pi generic, and the unique subspace corresponding to pi, we call it the Whittaker model of pi. And here we know that this definition really depends on the choice of your character on this unipotent group. Since in this talk is fixed, so I'll straight away call this Whittaker model of a irreducible representation. And this one has nothing. I couldn't do anything to it, but I would like to say that the results on this page is indeed due to Sergei Garfan in his 1970 paper. What he showed is that for every irreducible generic representation of the GRN, there is a unique element inside the induced representation space from the maximum unipotent, which is a function on G. So this J sub pi is a function on G, satisfying these two properties. The property 2 is essential here, which just states that this kind of function satisfies so-called UN by equivariance. And the first property is indeed some normalization property to ensure it is really unique. Or we can say like there is this unique function up to multiples of scalar satisfying this UN by equivariance property. As we will see later, we will interpret this Bessel function as some matrix element of G for some special types of representations, and some normalization constant may appear. I'll go into deep about this topic. And an interesting result of this function is that, shown by Sergei Garfan, is that this function only supported on certain Gauss cell of the group GRN. So namely, because by Broad decomposition, like the group GN can be like written into the disjoint union of all the double cosets in this form. But this Bessel function only supports on certain types of the Broad cell. Namely, it is anti-diagonal blocks of the matrix. And well, for GL2, there's only like two cases, like the anti-diagonal matrix and the diagonal matrix. But for GLN, like we have more supports of this this Bessel function. in this talk, I will present like some explicit computations, like the integral representations of Bessel function as a big cell of the GLN, which I'll explain in a minute. So here is some here we first consider like Whittaker functions over GL2 by using the Whittaker models, and then we see that for general linear groups we can define something similar. And well, if we move to some recent development into representation theory, actually this can help you to classify all the irreducible representations of your finite group GLM. So namely, that's an observation by Charles Curtis in 1990s. Find these factorizations of this unipotent Hecke algebra, which consists of all the Bessel functions. And the addition on this complex algebra is addition pointwisely. And the multiplication on this complex algebra is just the convolution on this group. Actually, as shown by Garvan-Grieve and Steinberg, this product or this convolution product on this complex algebra is commutative, which corresponds to the multiplicity one property of the Garvan-Grieve representation. They are equivalent. And this diagram here actually says that, like, let me start explaining this notation first. So T is a maximal torus in the group, which can be split, which can be a maximal split torus, which can be identified as a diagonal subgroup of diagonal matrices, or it can be, because this finite field FQ is not algebraically closed, it can be some non-split torus. The point is that this construction works for arbitrary maximal torus of the group. And this theta hat is merely saying the linear extension of this character theta to this complex group algebra of your maximal torus. And indeed, Curtis showed that not only for GLN or FQ, but arbitrary finite Chevalley groups, this homomorphism from this commutative Hecke algebra to complex numbers are classified by so-called geometric congruence classes defined by Deligne and Lustig. I will not explain what it is because actually this can be calculated explicitly in terms of Bessel functions, which I will explain later. And he showed that there is a factorization. And this homomorphism from the unipotent Hecke algebra to the complex algebra of the maximal torus is only determined by the geometric congruency class of this maximal torus, which is so-called Curtis homomorphism. And this construction provides a way to classify all irreducible representations of finite Chevalley groups. However, indeed I cheated here a bit because Curtis used Deligne-Lustig's like a theory of green functions, which use the algebraic sheaves. So actually the base field here is the algebraic closure of the algebraic field instead of C. But as we know, by comparison of fundamental degrees, actually these two fields are isomorphic. So it's free to write these two notations interchangeably. And like in my work, I don't really going into the arithmetic sheet, so I'll just write C here. But one point is that explicitly speaking, this one-dimensional representation of the commutative algebra is indeed determined by the Bessel functions. And actually, this is already observed by Garland and Gray. So the value of this ft theta can be expressed in terms of values of Bessel functions. And for some special case of this maximal torus, Charles Curtis actually proposed the following question. Namely, we find explicit values of this Curtis homomorphism, given the situation that this maximal torus is split. In other words, we can just fix that to be the subgroup of diagonal matrices. And this question he proposed like in his recent notes in 2015. My recent preference is to calculate this Curtis homomorphism when T is exactly maximal split torus for some special values, namely its values on big Bohr cells. So that's why the title of my preference is quite far away from looks far away from integrable systems and the title of my talk today. But indeed, the original motivation of my work is due to this picture here. So I think I should give one slide or two to explain what really happened. So as I explained, this problem of explicit computation of Curtis homomorphism indeed reduced to the computation of Bessel functions. And since we are simply working on the maximal split torus, as Charles Curtis indicated, so the generic representations we are really interested in will be principal series representations, which, as we see previously, it has it studied very well on the real numbers. And for simple case over finite field like GL2 and the affine group, we affine group we have some explicit interpretations in terms of group Kloosterman sums and Gauss sums. So that's something we would like to go for. So yeah, I guess this notation is quite natural appearing here because for the Borel subgroup, again, the lower triangular matrices is defined by this product of multiplicative characters over the finite field. And here we don't really specify what are these characters. Well, it can be trivial, like or like different characters, high I and high j. They can be like equal or distinct or not. We do not specify this at this moment, but in practice, actually, actually we are more interested in like we would like to have this multiplicative characters high to be distinct, which gives you a irreducible representation. Because without specifying this multiplicative characters, these representations can be irreducible, and not always constituents will lie in Garland and Gray. But it doesn't really matter if you you can just assume that this highs they are distinct. And we consider this induced representation, which is so-called principal series representation of the general linear group. So again, we would like to find the Whittaker vector or of this particular representation space, or like at least for certain irreducible constituents that lies in Gamma-functions representations. And the answer is quite simple. The answer is quite simple for this principal series representation. Namely, if we consider Broussard decomposition of this sphere, we're just saying that this Whittaker this particular vector in this representation space to take 0 on all the Broussard small cells. On the Broussard big cell, we're just saying that it's determined by the character of the maximal unipotent group, as I show on the as I show on this page. So it's a quite simple solution, but as I show in my as I show in my preparation, actually this works. This is indeed the eigenfunction under the action of maximum unipotent. Or in other words, this is the Whittaker vector of the principal series representation. Simple enough, but it works. It is quite surprising that because this kind of construction doesn't work for other types of generic representations. And for principal series, yeah, that's a very good point to start because it's not very complicated. So since we have found our Whittaker vector, we know this. We can define a matrix element for this pair of two vectors in the representation space. Namely, it can be arbitrary f in the representation space, but we want that to be paired with the Whittaker vector. And explicitly, by this, by definition of, by our construction of this Whittaker vector, we know that the sum of the finite group only takes value on the Broussard big cell, which also can be interpreted as the sum over the maximum unipotent group given in this form. And we also, like in the spirit of quotient, because also Garifan, we want some UN by equivariant function. So we just take this f to be the Whittaker vector again. And we call this definition, and we call this particular matrix and this function over the finite group GLNFQ, the Whittaker function. Well, of course, associated with this principal series representation. And since we know that we already take this f to be another Whittaker vector, so we know that this one is actually U by equivariant. So as I explained, like due to the work of Garifan, this capital psi, this psi GLN is U by equivariant. So of course this is unique, but up to some constant. We will just need to determine what is the normalization constant. And well, it's not hard to compute. And yeah, I mean the value of this function at 1 is not hard to compute, but it may take some effort to yeah, well basically the technical point would be like this irreducible constituents of this principal series representation, because in general it can be like, because this representation itself in general it can be reducible, but anyway, if we think our representation is itself irreducible, then we can simply remove this s. We're just saying that the Bessel function of irreducible principal series representation can be identified with this matrix element. we have write down, which has this very simple the simple integral expression due to the construction of the Whittaker vector. And moreover, by using this matrix element, by using this interpretation of the Bessel function, we actually computed what it is. And well, on a big draw cell. Namely, if we take our X to be like anti-diagonal matrix, we have the explicit formula for this Whittaker function, evaluated at this bra big cell or bra open cell, and it has this structure. Here, I was a little bit lazy when writing down this notation. Actually, this notation indicates that we are summing over this following diagram or this following graph. I would like to call it Gamma setting graph here. Well, it's okay. You couldn't see it, but I would like to call it the Gamma setting for some reasons. But here we see that for this multiplicative counterpart, these sums are taken over all the arrows appearing in this diagram. And for some reason, we make the convention that for the horizontal for vertical arrows, they all contribute plus in this expression. And for horizontal arrows, it contributes to minus to this expression. And this arrow, it means like this rational function of these two variables. And the value of this Whittaker function evaluated at a big cell is actually summation, or you can think of as an integral over finite fields as a summation over all the vertices Ti, or all the vertices Ti, Tik. And with some contributions of the multiplicative part. Actually, this rational function here also has a meaning that we are viewing this one as the product of diagonals in this Gamma setting graph. So which means that for each character k, it means the kth diagonal of this Gamma setting graph and quotient by the k minus first diagonal of the graph. So there is a very transparent interpretation of this particular values of Whittaker function associated to principal series representation. This formula we obtain for finite field due to all the constructions I explained using representation theory of the Chevalley group. It's interesting because we have exactly the same formula, which means it shares the same Gamma setting graph as the Gerald and R Whittaker function, which is constructed by Cousin originally, like, well, his construction already works for R plus Gerald and R. And this formula here is initially proposed by Xuantong while specifying this lambda k, these multiplicative parameters, to be 0. And then you get this this summation over the arrows. And if you, well, since it's exponential, you can think of as e to the tk plus 1i quotient by e to the power of tki. So it's exactly the same as, so it has exactly combinatorial interpretation in terms of this reference setting graph. And for the multiplicative part, it's the same. So actually, these two different looking functions share the same combinatorial picture. And we also know that this GRN R Whittaker function due to Rossimov-Lebedev and Oblazin's result, it can be identified as the Whittaker function, which is the invariant function under the maximal compact group of GRN R. So actually, this function is only determined by its value on the maximal, the Brouwer open cells GRN R. And it has this form. And in particular, for n equals 2, we come back to GL2 again. We know that this function, this GL2 Whittaker function over the real numbers can be identified with this the solutions to Bessel equation under a certain specification of the parameter and the value of the argument. Which shows that actually different functions appearing in the different contexts of representation theory, they may still share the same, share some same combinatorics. So here comes to the conclusion of my talk. So we consider several finite field analogues of special functions over, well, say the real numbers. And in particular, we identify Gauss sum as matrix coefficient of the finite group over the finite field. Also, one can mention that the similar result can be shown for Archimedean field because the moreover, actually, that induced representation is again irreducible over the real numbers. I will not prove that in my talk. And another point is that, yeah, so we start with like SR2R, but then we see that for GL2 or for GLN, the Kloosterman sums are indeed finite field analog to the Whittaker functions. And they share some representation theory in the spirit of Whittaker models. But as I explained earlier, this GRN R Whittaker function is indeed supported on the big Brouwer cell, but the GRNFQ is not. So, an interesting question following this idea, following this pathway is that what happens for the values of Whittaker functions over the small cells? Or like, can we define a notion of parabolic Whittaker functions as the values of GRN Q Whittaker function on the Brouwer small cells? That's a question to, well, that's a question to study. And what kind of representation theoretic what kind of combinatorial interpretation and what kind of geometric interpretation it should have comparing to the pictures I presented throughout my talk. That's a very interesting question to work on. Moreover, as I showed on the GL2 case, both Whittaker functions over finite field and the real numbers, it has this main invariance integral representation, namely they are the integrals of products of Gauss sum. And due to the work by Rossimov, Lebedev, and Oblazin, they show that actually the main invariance integral representation exists for, well, they computed that for GRN R Whittaker functions. But it's still not yet known that for general N, what happens for Whittaker functions over finite is that expressed in terms of like summations over products or rational functions of Gauss sums. This one we don't know, and which which is another further direction when we consider following this. Well, if we're trying to interpret the special functions as associated to representations over finite Chevalley groups. So that's the end of my talk. Thanks again for attention and coming from the view.
Okay, thank you for your talk. Any questions or comments?
I have one question. So if you show the Giventhal formula, here you have in Archimedean case all arrows go with pluses.
Yes.
And in finite field case you have minus. Is it something you do on purpose or it can be unified?
Oh, well, yes, very good question. I'm glad you asked. Actually, that's something only due to my convention, because as you see, we are working with GLN, so actually we can make some amendments to this argument. So if we put like x1 minus x2 plus x3, like so on and so forth, for this argument, actually we can show that all the minus sign here will become plus. So it's a matter of choice of the argument you like. And moreover, you're working on GLN. So like you can do the adjustment to that argument to the Whittaker function if you want. So in some sense, that's yeah, that's why I started with GLN, because yeah, there's this kind of flexibility. Yeah.
I really a bit wonder, do you consider representation theory of Chevalley groups or the complex field or the finite fields? Your group is defined by finite fields, GLFQ.
Yes.
I just wonder that there is a really extensive literature about the story about representation theory of Chevalley group or finite field. This is Lewistic, a lot of peoples, and they compute the characters of this representation and many other things related to representation theory.
Mm-hmm.
Is it related with somehow with your representation of Chevalley group?
Oh, okay. Yeah. First of all, yeah. Thank you so much for the question or comments. First of all, the representation I consider here are all representations over complex numbers, as I showed in some slides. Yeah. For example, this slide, because I'm considering all the functions from the finite group to complex numbers, so which is a complex representation space, and yes, and you know that for complex representations of finite Chevalley groups, there are many interesting theories. This is something I'm interested in, and well, indeed, the representation theory okay, so like modular representation theory over finite field also appears like in my calculation, because like if we want to determine this integrand explicitly, we need to see like we need to see like some well, geometry over this finite group, this UN, so which correspond to like representation theory or matrix element over this finite geometric object.
Well, and I just wonder about orthogonal polynomials for Chevalley groups.
Mm-hmm.
It was some theory of Dunkel, and he really introduced his operators, Dunkel operators, from the study of representation, orthogonal polynomials of Chevalley groups. Do you have some kind of orthogonal polynomials here?
No. I haven't come to the study of like orthogonal groups and the relation with this. for this matrix element of complex translations. No.
Okay, no more questions, probably from Zoom. Okay, if not, let's send the speaker again.
Thank you very much.